cup of coffee will always cool down. It will never spontaneously heat back up on its own, pulling warmth out of the air around it. An ice cube left on a counter will always melt into a puddle, and that puddle will never refreeze itself back into a perfect cube. Drop a glass on the floor and it shatters into 100 pieces. No one has ever watched those pieces leap back up and reassemble themselves into a glass. Something about the universe seems to run in only one direction, scattering and spreading no matter what we do. Physicists in the 1800s gave this one-way drift a name, entropy. But for decades, nobody could explain why it only ever moved forward, never backward. Why does the universe seem to play favorites with chaos? The man who finally cracked it was Ludwig Boltzmann, an Austrian physicist born in Vienna in 1844 in the dying hours of a Mardi Gras ball on the cusp between Shrove Tuesday and Ash Wednesday, a fact he liked to blame for his own wild swings between joy and despair. He was short, stout, soft-hearted, and surprisingly artistic for a physicist. As a boy, he studied piano briefly under the composer Anton Bruckner, and as an adult, he found his clearest thinking on long hikes through the Alps. None of that softness showed up in his science. In the 1870s, most physicists doubted that atoms even existed at all. They were far too small to ever see, so respected thinkers like Ernst Mach dismissed them as a convenient guess rather than physical reality. The rivalry became personal. In 1894, Mach took the very chair in Vienna that Boltzmann had hoped to inherit. Boltzmann pressed on anyway, determined to prove atoms were real using nothing but probability. Boltzmann's idea was this: any physical system can be arranged in many different ways, and some arrangements are simply far more common than others. Start with something small. Flip 4 coins. There is only one way to get 4 heads, and only one way to get 4 tails. But there are 6 different ways to land exactly 2 heads and 2 tails. If you flip those coins at random, you are far more likely to land on a mixed result than a perfectly uniform one, simply because more arrangements lead there. Now scale that idea up to something we can actually picture. Imagine a bedroom. There is exactly one way for every sock, book, and shirt to sit in its perfectly tidy spot. But there are millions of ways for those same objects to end up scattered across the floor. Toss everything around at random for long enough, and you will almost always land on a messy arrangement, simply because there are vastly more messy arrangements available than tidy ones. Nobody is pushing the room toward chaos. Chaos just has more doors leading into it. Boltzmann applied that same logic to gas molecules bouncing around inside a container. Each possible arrangement of positions and speeds for billions of molecules is called a microstate. A handful of microstates look orderly, with all the fast-moving molecules bunched into one corner. But the overwhelming majority of microstates look spread out in uniform, because there are far more ways to be spread out than to be clustered. Boltzmann defined entropy as a measure of how many microstates match a given visible overall state. A tidy, ordered state has very few matching microstates, so it has low entropy. A messy, spread-out state has an enormous number of matching microstates, so it has high entropy. He captured this relationship in one elegant equation. Entropy equals a constant multiplied by the natural logarithm of the number of microstates. That constant is now named after him, the Boltzmann constant, a tiny number, about 1.38 times 10 to the power of negative 23 joules per Kelvin. It acts as a bridge, converting a pure count of arrangements into the everyday quantities of heat and temperature that we can read off a thermometer. This is why systems drift toward disorder over time. Nature does not prefer chaos for its own sake. It is simply that disordered arrangements vastly outnumber ordered ones. So left alone, any system will wander toward whichever overall state has the most microstates available to it. Boltzmann fought for this idea for his entire career, ridiculed by some of the most respected scientists of his era. He died in 1906, before he could see it fully vindicated. Within a few years, the physicist Jean Perrin's experiments on the jittery motion of pollen grains suspended in water proved that atoms were real all along, exactly as Boltzmann had insisted. Boltzmann's constant did not stay confined to gases bouncing in a box. Every transistor inside your phone obeys equations built on it because heat and electrical noise inside semiconductors follow the very same probability rules as bouncing molecules. Chemists use it to predict exactly how much faster a reaction runs when you heat it up, since warmer molecules explore far more microstates every second. Engineers designing engines and refrigerators run straight into the same constant. It sets a hard ceiling on how efficient any heat engine can ever be, which is why no car, power plant, or refrigerator has ever reached 100% efficiency, and why none ever will. Decades later, the scientist Claude Shannon borrowed Boltzmann's exact logarithmic formula to measure the entropy of information itself, the uncertainty packed inside a string of digital bits. That borrowed idea now underlies digital compression and modern communication, quietly deciding how small your photos and videos can shrink before they start losing detail. The coffee cooling on your desk, the heat ticking out of your phone's processor, and the file size of a compressed video are, underneath it all, three faces of the very same statistical idea that Boltzmann spent his life defending. So that coffee, that melted ice cube, that shattered glass, none of them are being pulled toward chaos by some hidden hand. They're simply following the numbers, the same way they do every single time in every corner of the universe. What other ordinary rules of daily life might just be statistics wearing a disguise? To uncover the full story of the man who rewrote the rules of reality, head over to our complete documentary on Ludwig Boltzmann. It is waiting for you on the channel. Simply click on the video on your screen right now to dive in. The link is in the description as well.